Hi, welcome to this video titled, Inverted is not upside down. Sounds like a very vague title. In this short video, we will discuss the idea of, quote, inverse systems commonly seen in control theory without using complex equations. We'll see examples ranging from cars to the human brain, and find that the idea is seen everywhere. Inversion is not about flipping the world. It is about asking a different question. When we hear the word system, we might think of order, social structures, computer systems, or machines. Right now, you are probably reading or hearing this on your computer system. However, engineers use the term system very precisely in control theory. For a control engineer, a system accepts inputs and produces outputs. Our core job is to choose inputs to achieve desired outputs. This fundamental framework powers almost all of engineering. Consider the car as a system. The inputs are steering, throttle, and brake. The outputs are speed, direction, and motion. Our goal is the desired motion on the road, which is control theory in plain sight. It is crucial to remember that every system has limits. Some motions are possible, but others are fundamentally impossible. No skill can override the laws of physics. The trackable set includes all motions a system can perform. This set depends on the system's design and underlying physics. A race car's trackable set is different from a sedan's or an aircraft's, and it is easy to see that a passenger aircraft can never perform the complex and breathtaking maneuvers a fighter aircraft would perform, and then there would be maneuvers even the most maneuverable fighter aircraft may never perform. Conversely, the untrackable set contains motions that no control input can produce. This is determined by the system structure, independent of any operator skill. For a race car, the untrackable set is a collection of curved racing tracks that the car can never follow, no matter how skilled the driver is. Control design involves choosing the right inputs to achieve desired outputs while respecting the inherent system limits. This process forms the heart of control engineering. It is easy to see that most, if not all, engineering notions can relate to the idea of a, quote, system, and in these systems, getting the desired outcomes or outputs by choosing appropriate actions or inputs is often the end goal. Finding such appropriate actions or inputs to achieve desired outputs is what the control engineers would call, quote, control design. Now, let's look at system inversion. Normally, we think inputs lead to outputs. Inversion asks the opposite question. Given a desired output, what input is required? Instead of guessing inputs, what if some other magical system told you exactly what to do? The inverse system, theoretically, acts as a perfect mathematical driver or pilot. It outputs the exact inputs you should apply to achieve your goal. This concept is both powerful and potentially dangerous. Yes, magical, also dangerous. For some peculiar type of systems, control engineers complain that these contain something called as non-minimum phase zeros, and rightly so, since these could turn things upside down in the real world. The inverse, even if defined for such systems, may cause undesired behaviors that could range from funny to dangerous. Controls folks quite euphemistically refer to this as unstable behavior, or simply instability. So in reality, inverse systems do not always exist. Some can cause instability or behave badly. Control theorists call this instability. Engineers on the field say it don't do this. A major limitation is that the inverse system operates in an open-loop manner, and control engineers like to refer to this concept as feed-forward. The inverse system, therefore, only tells you what inputs would lead you to desired outcomes. And it would particularly not help if you deviate or lose track from your desired outputs. That is, it provides no correction if things go wrong and assumes perfect knowledge, which often fails in imperfect worlds. At this point, a system by the name feedback controller comes to the rescue, which corrects the deviation that may be a result of uncertainty. Feedback is crucial to survival. It measures deviation from the desired path, corrects errors, and handles uncertainty. This corrective process is essential for navigating real-world situations. Think of the feedback controller as you, the driver, actively trying to push through the traffic, uncertainty, even as the map application on your smartphone, feedforward controller, tells you how to navigate from source to destination. The map app is feedforward planning, while the driver acts on real-time feedback on the road. Together, they enable reliable navigation. One plans, the other adapts. For the reasons best known to mathematicians and control theorists, there are two types of system inverses known by the names left inverse and right inverse. The one discussed previously is the right inverse, which is useful in determining control inputs. The left inverse, on the other hand, tells you what inputs caused a certain undesired outcome, the task of input reconstruction. Think of detectives trying to reconstruct events that preceded a crime. In summary, a right inverse helps you getting things done, while a left inverse helps you understand what went wrong. Some systems can have both right and left inverses, while some may have only one of them. It all depends on the number of inputs, say steering, brake and accelerator, and outputs, say speed, direction and position on road, a system has, and on the relative degree. When an input is applied to a system, the outputs respond, although with some characteristic delay, which could very well be zero. This delay is characterized by a quote relative degree and must be accounted for while issuing control actions, akin to a car driver foreseeing a turn and taking anticipative action by reducing speed and steering appropriately. The idea of relative degree can be seen as originating from the delays in either the inputs or outputs of the system and must be accounted for in both left or right inverse situations. For a system to have an inverse, it should have a well-defined relative degree, and vice versa. In essence, relative degree is a multi-way delay between a system's inputs and outputs, and this delay must be anticipated, just as you brake before a turn, not while actually performing the turn. Some systems cannot be fully inverted because they have too many outputs or too few inputs, or if the time delays mismatch. This is a structural limitation, not a failure. Take the quadcopter, for example. It has 4 inputs, thrust and moments, but 6 outputs, position and orientation. It lacks a full right inverse, yet it still flies. The quadcopter flies by prioritizing its outputs, trading precision for safety, and aggressively using feedback. Control, ultimately, is about making smart choices under constraint. Selective or prioritized control means focusing on what matters most and allowing other objectives to relax. Changing priorities on the fly is a sign of intelligence in a system. For a wall-following robot, following the wall is one task, but avoiding a collision with the wall is another. Safety always overrides the mission, as a living system will prioritize survival first. Inverse systems are still systems. They have their own inputs, outputs, and dynamics, and they can be unstable. Inverting a system does not make complexity vanish. Neuroscience offers a surprise. Humans learn inverse models through repetition and error correction. This concept is not only engineering, but also deeply embedded in biology. Motor learning, seen in writing, sports, and tool use, involves adaptation to new devices. When you get a new bicycle, your brain quietly rewires to accommodate it. The brain acts as an inverse model builder, mapping desired motion to necessary muscle commands. It learns through trial and error and refines itself with feedback. Your nervous system is a control engineer. Control theory, neuroscience, and robotics intersect when asking the same fundamental questions using different terminology and approaches. Understanding these concepts leads to better controllers and more adaptive robots, offering a deeper understanding of human capabilities. Inversion is not upside down. It is a source of insight. The key takeaway is that not all systems can be inverted, and feedback is essential to make inversion usable. Learning systems blur the boundary, showing where control becomes more organic than mechanical. In closing, inversion is structured thinking, not magic. It requires humility about system limits, which is what defines a good engineer and makes robust systems.